Good evening. Oh, thanks. I will spend 1 minute about the exam, but I don't want to spend a lot of time discussing that. I will spend a lot of time on it, but it will be regrading the exam wrappers. So if you have not seen the announcement, I want to motivate people to use this as a study tool. I think you should do it whenever you have any exam. It shouldn't just be motivated by points, but I will motivate you by points for this exam. Go back, look over the exam, see what you did wrong, why you did it wrong, what the right answer would be, and why that's the right answer. One of the 2 pieces of paper that you guys got is the exam 3 wrapper. It's not the exam. Why is the exam 3 wrapper on the back? Front. So I guess I didn't update everything on this exam wrapper from last semester. So this is our exam wrapper for this exam, the piece of paper that you guys picked up. The point is for you to go back. If you turn an exam that's been you worked through that doesn't have one of these, you won't get credit. So let's just don't do that, please. Read through this. It's really critical to me that you're doing this as a reflective process. I know for you a lot of it's about getting the points, earning some more points back. For me, it's about a reflective process and you becoming stronger because you're reflecting on your mistakes. Mistakes are the first opportunity to learn, and if you're not using it as an opportunity to learn, then you're not going to get nearly as far. So I'm trying to encourage that process. So please read this carefully, complete it, staple this to your exam. I need to have your exam or else I can't say what you are working to earn credit back for, what you missed. You will probably, some of you saw too, that I posted the exam key, so it has what the right answers are for the multiple choice. That way you can look and see what you got wrong. For multiple choice, you have to say, why is my answer wrong? What would the misconception be? What would the right way to get the answer be? And then what is the right answer? And kind of justify that all along the way. If I don't see your process, if you just give me an answer, you didn't earn the points back. Then you kind of avoided the whole process, so I won't give you credit. I'd say most people earn about half of the credit back that they can on these exam wrappers because they either don't have a full grasp of the concept still and try to do the problem. They don't use their resources. They don't work with each other. They don't come to office hours maybe to the extent that you would need in order to fully grasp it. It's not easy if you got a score you're not happy with to get all the way up to earning half of those points back. I'm not saying it is. Just kind of giving a relative frame of reference. Typically about half the points are earned that can be earned back. So that's, I guess, a quarter of the gap between you and 100%. You can earn it all the way up to 50% to get that gap in half, right? So if you got a 75, you can earn 12.5 points back. That's what I'm offering for you guys. It is due next Wednesday at the start of class. If I don't have it at the start of class next Wednesday, then it does not count. You can turn it in before then as well. But please come to office hours. Please form study groups. Work with other people who have done it, done those problems, and have maybe a better idea. But if you do that, make sure that what you turn in looks like your own work and is your own work and has your own understanding built into it so that I don't question at all whether you just wrote down someone else's answer. Just don't put me in that position. Just make it clear that it's your own work. Any questions? Yes, Nigel?
You said next Wednesday?
Next Wednesday, 3/6. That's what's on there, right? In bold? Just making sure. I didn't put everything on there that I thought I did, right? I thought I changed this to exam 1 wrapper for 1403, and it says exam 3 for 1402. So that's not on you, that's on me. Okay. Second, logistics. For our supplemental instruction, we put a lot of effort in every week to choose an activity that we think will help bolster your progress in this class. The material is going to get more and more mathematically challenging as we go. We intentionally have it on Thursday nights right beside the Math Assistance Center on the 4th floor of ETAS. If you have any trouble, go in there before or after the supplemental instruction, or use that as one of your resources. We have typically about 10 to 18 people come on Thursday nights. This Saturday from 2 to 3, we had 1 person. And while it may be helpful for that 1 person, we want to make sure that we're utilizing our resources to help the most people possible. So I need to hear back from you guys. Should we continue doing a Saturday supplemental instruction in the middle of the day? Or should we change the time of that to some other time and re-poll and find another, maybe Tuesday night at 8 to 9:30? I don't know. Find another time that would work Or maybe during the daytime during the week.
Could we do a poll on that?
Yeah.
I just want to make a suggestion. A lot of the classes are divided up between Monday, Wednesday, Friday, or Tuesday, Thursday. So it's hard, like, you know, if you have all your classes Monday, Wednesday, Friday, and they're only on Tuesdays and Thursdays, so like maybe one on each of those schedules.
Yeah, so the challenge is we're going to be doing our supplemental, our Friends of Medicine, or whatever we're going to call it, the seminar series right before class on Wednesdays. So then that blocks out 4:30 until 8:30, whatever it is, on Wednesdays. So if people are taking a night class because they have other things during the day, then that only leaves Tuesday night, because Monday and Wednesday night we have this class. So I'm trying to figure out the best way to do that. But if we have the most people respond, they can do it another day during the day, and it's, you know, Wednesday or something, then I'm happy to do that.
Maybe like maybe a little bit earlier on Saturday, because every Saturday I go to work at 3, so I can't like do something for an hour because I'm driving to work like around 2:30.
So if we do another poll, and Saturday morning is an option that we put on there, and people respond to that, then we'll do that. It sounds like we need to do another poll though. Maybe I should do one more hand raise. Is the time currently available on Saturdays? Does that work for you? And will you go? Saturday 2 to 3:30. We're not going to keep it if people are not going. So
It works better than Thursday.
okay.
I'm not coming
Yeah,
up
Monday through
So
Friday.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15. So we do have 13 people. So is it just maybe the last week or two didn't work out well with people's schedules?
Yeah.
Called in.
Okay, so I'm not, and it was the week after the exam, so maybe that has something to do with it. So that is honestly more people than I would expect to get in any other time slot. So I think we'll keep it there. And if you work at 3, you can come on for the first half hour, 40 minutes, if that's possible, or go to work early and then, because you can connect on your phone. I don't know, we can talk about it, there might be other ways.
I'm gonna be driving, but yeah,
So for now,
Will you take another poll? If the people that are there, like that do Saturdays, can they do it in the morning, like at 10?
Yeah.
okay, so who cannot do it if we shift it earlier by 2 hours or so on that Saturday?
I'll try and do
We just raised Saturday 2 hours earlier, so starting at noon instead. Can anyone not do it that all just raise their hand? Anyone not do it that just raise their hand? Yeah, okay. So are we in agreement that shifting it to 12 to 1:30 will still support most people and possibly a couple more people? Saturdays, 12 to 1:30. All right, Josh, that work for you? I should check with the person running it as well. Great. Okay. And has this not been up the whole time?
No. It's been on.
All right. So activity 57. If you guys completed this, you will have found that this is very much in line with what you're doing in lab. So we're going to build off this today. So hopefully we'll be able to do the beginning part pretty quickly, and then we'll be able to start talking about some more challenging things. If you have not turned in 57 and want to do so, do it now. Okay, so go ahead and take a look at this first table. It's on your phones as well. Once you've decided your answer, go ahead and chat with your neighbor, confirm. All right, a couple more clicks. We are split. All right, we are not in agreement at all. We're actually split 2 to 1. Did you talk to someone that didn't agree with you? Can we do that? Does it work when I say that? branch a little further out. Find someone who disagreed with you. We're split between B and C. B and C are the two answers. All right, 10 more seconds.
I'm just saying,
Click in your final response. Come on, buddy. We got from 2 to 1 to 50-50. All right. Is anyone confident?
Reaction rate should be like half.
Okay, so you're saying proportional. If you close this up.
So if you compare experiment 1 to experiment 3, you cut NO in half. The initial reaction rate doesn't get cut in half. Instead, it's 4 times as much. Or if you work the other way, if you double the amount of NO from 3 to 1, it quadruples the initial reaction rate.
Which is 2 raised to a power of 2. Okay, so we have been having you guys work with this a decent amount. I want you to picture what this actually looks like. Where's this data coming from? So we have this experiment where we put together these two gases, and if we control the exact amount that we start with, and then we go to the stopwatch and figure out how does the concentration of the product increase over time, or you could say how does the concentration of the products decrease over time. If we monitor that, we can find the initial rate of reaction. Then we're going to say, well, what happens if we change one of those two reactants' initial concentration? Does that influence the rate of reaction? So then we do experiment 2. Which one did we change between experiment 1 and experiment 2? So we just use a lower concentration of oxygen, but we use the same concentration of nitrous oxide. And then we said, what happens to the rate? We measured that. And then we do a third experiment, and we say, well, I really want to know what happens if I only change the concentration of NO. Does that influence the rate? In order to do that, we have to keep this constant and only change one of our variables, or else we can't tell what the effects came from. So if we do that, we decrease the initial amount of NO. We see that the rate does change, so A is not going to be a correct answer. And then choosing between these two, if we cut it in half, or the way that I think Colin mentioned, you could look at the other way and say, well, experiment 1 is twice the concentration of experiment 3. Is the rate twice experiment 3? The answer is no. So this is absolutely an exponential relationship between those two. What would you expect to see for the rate of experiment 3 if it was proportional, B?
5.0 times 10 to the negative 7.
How do you guys feel about that? 5.0 times 10 to the negative 7th molar per second would be this rate if the reaction rate was proportional to the concentration of NO. It would be exactly half the concentration and half the rate, but that proportionality would hold true. So what we're going to spend a bit of time on this today, but this is exactly what we worked out in the packet, so hopefully you can make the connection between that. If you have not completed Activity 57, once again, a really valuable resource to practice this. They go through and look at how the reaction rate is proportional or not proportional to the concentration of reactants. So today my learning objectives for you guys are to predict how the rate of reaction depends on the starting concentration of the reactants. That's what we call the rate order. So then you're going to be determining the rate orders using experimental data, which we've hinted at there, but we haven't explicitly stated yet. And then once we've done that, we can determine the full-on rate law, which is the expression, that equation, the rate equals K times the concentration raised to the rate order. And then that allows us to also solve for K, our rate constant. If you notice, we're going to be very particular this semester about lowercase and uppercase letters. Lowercase m versus uppercase m, a big difference. Molality, molarity. Lowercase k, rate constant. Uppercase k, equilibrium constant. All right, so let's be really careful with our units and describing them. And then we're also going to go back and refresh a little bit about the relative rates of formations of products and consumption of reactants, and how that relates to the rate of reaction, which is activity 36. So if you have not yet picked up your activity 36 that you completed, please do so at the end of class. I've given a lot of feedback, and I probably took way too long grading these. At first I thought I'd just be kind of checking them off, but I think it's valuable for you guys to get feedback, so please use the feedback I write, otherwise I'm just kind of like wasting my time. And I want us keeping in mind how the stoichiometric coefficients are related to all of this. Josh, is there anything else I need to address? Okay. All right, so let's go ahead, and I want you to click in the rate order for oxygen. This is the same reaction we just looked at. This is also question number 1 that you were working from before. But I want you to determine the rate order for oxygen. I think you guys kind of we determined the rate order for NO. So go ahead and just click in the rate order for O2. And remember, we have lots of assistants in here, so raise your hand or ask around if you have questions on how to do this.
I thought you were going to say something. I was like, okay, I'm ready.
Yes. And it would be live.
I understand. Yeah. Like, it's
All right, a couple more seconds to click in your rate order for O2.
So you have to find it. So pick one and find.
All right, I'd like to hear from a new voice. Can someone share with me how we use the data here to determine the rate order for O2? Go ahead. Nice and loud.
So since we're trying to find a rate order for O2, we didn't find concentration staying the same
For what?
for nitrous oxide.
Okay.
So for 1 and 2,
So experiments 1 and 2,
yes,
there's no difference in the starting concentration of NO.
yes. Okay, so take the ratio of experiment 2's concentration of O2.
To experiment 1?
Yes. And then do the same ratio for, yeah. And then I saw that it doubled in both cases, so I said that the rate was
So if we change the initial concentration of O2, the rate changes proportional to whatever that change is. So if this had been a 3-fold difference, we would expect to see a 3-fold difference here. If it had been a 7-fold difference, it'd be a 7-fold difference in the rate, the initial rate of that reaction. All right, so don't get caught in the idea of, oh, if the rate doubles between those two, it means it's first order. Just a lot of times doubling the concentration is an easy way to see, does the rate double? Okay, so just be really careful about that. So you said that the rate order was 1, and I believe most of the class agrees with you there. We had most of the class, so that's great. So then what is the rate order, it's called the differentiated rate law. What is the whole differentiated rate law for this reaction? Go ahead and write that out. There's the generic rate law. So this is called the differentiated rate law. So go ahead and write this out with some more specifics in there. What are the two things you can now fill in? Two rate orders, M and N. Used to be two professors. I taught this class. David, what is the more specific rate, differentiated rate law for this reaction? Hey guys, can we have Nabil? Janesh? Come on, help me out, guys. Go ahead.
So R equals K times the concentration of nitrous oxide raised to the first, but I didn't put a 1 because it's understood, and then times the concentration of O2 to the 1.
Does everybody agree?
Goes to the 2.
Okay, so which one is to the first, which one is to the second rate order? Second power.
NO is 2.
Great, so NO is to the second power, it's second order. O2 is the first, and I wouldn't have R, I would write out rate.
Oh, okay.
Just a small quirk, but we want to write that out fully. So if I say what order is this reaction overall, we look at the sum of all the exponents. So this is the generic rate order for the reaction, and it's third order overall. All right, that tells us some stuff down the line about how we expect this reaction to proceed. All right, now I want you guys to find the rate constant for this reaction. I'll give you guys about 2 to 3 minutes to answer this question. Please raise your hand and ask for help if you're stuck, don't know where to go. Just make sure
I know. I gotta press something wrong. You know? Wow. No, I'm getting the same thing. Oh, it's a clipper? Kind of this. Like, mentally not.
If you're alive, you can your initial volume is final volume is the sum of all the flows. So you find your
I was leaning back on my bed. No, you're fine. Great. This means that's great. Now, is your rate that
we use that a lot.
Oh, by the way, I have your I did it, but like, we'll just
All right. How do we find the value of the rate constant? Ooh, John.
Okay, so the different concentrations and their exponents, we're going to, with all that's known, we're going to calculate that and get one whole numerical value. And then we'll just use basic algebra. We already have the rate. And
How do we have the rate? What are you talking about?
in our table. So what I did is I chose experiment 1.
Okay, so if we use experiment 1, what do you do with all that information?
Alright, so we know NO, the concentration of that, so of course we're going to type that in the bracket, and we know that's to the second order. And same thing with O2, we know that's to the first order, and we're going to do that multiplication and get the answer for that, and divide that by the rate.
Divide that by the rate or the rate by that?
Or the rate by that.
Yeah. Okay, so we isolate the variable. This is algebra, right? Isolate the variable. We know everything else. Did anyone pick experiment 2? Did anyone verify their answer for experiment 1 with experiment 2 or experiment 3? Did you find the same value for all 3?
I didn't get to experiment 3.
I did all three, yeah, it's the same.
Okay, and what did you find numerically when you did that? Bria? You found your rate constant equals 1. What units does that have? Should that have?
per over mole times
Per what?
1 over M squared times over.
It's like
I don't understand what
So here's one kind of, you know how you always look for like little keys that make problems way easier for you? This is one of them. If you think about the units, it will guide you. So a lot of times you might get given a rate constant and say, is this 0, second, or third order, the units will give it away. Because if you look over here, what are the units inside these parentheses? Molarity squared times molarity, so this is molarity cubed, times whatever units you have for the rate constant, which we'll figure out. And on the left side, we have molarity per second. So what does K have to be to make the units on both sides be the same? So let me clear all this out. So on the left side, we have molarity per second equals something, some units, times molarity cubed. So that has to be 1 over molarity squared times seconds. Understand how we got there? I'm not giving you a hard time. Good job, Caleb. All right, if it was second order overall, what would be different about the units?
Minus one of them.
It would only be m squared here, molarity squared. So that would be molarity times seconds on the bottom. If it was 0 order overall, it would be molarity per second. Right? So we know the units of rate are always going to be the same. We know the units of concentration are the same. The question is what order is it, and then we can kind of pull out from there. All right? And what's really important is that if you're not 100% confident in the experiment that you use and plugging it in right, you have 2 more experiments to do the exact same thing, and we should always have the exact same outcome. So what does all this mean? So this question.
So in the homework on when we talked about like using different experiments, it said that sometimes you can take the average of them. Does that mean that like sometimes they're not always gonna be the same?
The average of?
Like your rate constant. Like
so if you do a lab on this, you might not get exactly 1 each time you do it for your experimentally determined rate order. So then you might get 0.94 and 1.06. So if you do the same reaction multiple times, exactly you need to average those. So you should have the same rate order every time you do the reaction, but experiments aren't exact. And so you're going to have a little bit of variability. Very good question. All right. What I want us thinking about with these differentiated rate laws is a lot of times we're really interested in how fast the reaction happens. If we know something about how the reactants interact with each other, then we can figure out how the rate of reaction changes. This is the initial rate of reaction. Remember last week you were doing calculations in your workshop activity, the supplemental instruction activity, to find how the rates of one reactant compared to another reactant compared to the rate of production of product. All those things are tied together through multiple ways, but that rate is something that we look at how does the concentration of one relate to the concentration of another. Can we use the stoichiometric coefficients? Can we just plug in m and n as the stoichiometric coefficients?
No.
Sometimes they'll be the same. Most of the times they're not. So you always have to determine that experimentally. There's a lot of text. I think we'll come back to describing how the integrated rate law is used in a minute when we talk about the relative rates of consumption of reactants and production of products. So if you're unsatisfied with how we're describing that right now, give me a minute. So the second set of data is the bottom of your page. We're on to question number 2. It would take 15 more seconds to answer this question.
Yeah, but what it asks for. experiment in a perfect condition.
All right, a couple more seconds. Tyler, which one of these answers do you think is the best for describing the initial rate of reaction?
C.
Why C?
Because it doesn't start forming until in between negative 2,000 and 3,000 seconds.
No, that's a zero. That means that line's zero. Right. I think that the x-axis is going.
That x-axis is jacked, huh?
Yeah. Yeah. It should be A, but it's bigger.
Okay, so let's ignore the graph. Sorry, I guess when you copy and paste slides from one slide back to the other, sometimes Excel wreaks havoc on data. So if we looked at the data in the table, then can you describe why we might choose A?
Because that's the initial part of the reaction.
Okay. This is a very tough question. So that last set of data that we looked at, what was changing between each one of those experiments, and how does that relate to this set of data that we see here?
Oh, the last one they changed.
What concentration was changing?
Only changed about.
So this might be, is this experiment 1? Experiment 2 or experiment 3?
It's one.
Why is it experiment 1?
They're both the concentrations are the same, and they are in experiment one, they're both the same.
Okay, so experiment 1, we started with 0.100 molar of each of our two reactants, NO and O2, correct? And the initial rate of reaction could be determined by looking at the slope, the rate of change of concentration of which one of those two reactants. How do we determine the initial rate of reaction? Talk to your neighbor. How, with this information here, do we determine the initial rate of reaction? That is the rate, yes.
Is that how we determine it?
For which one? It's a lot of different concentrations. They're all So, Annalise and Riley, can one of you share your thoughts on how we determine the initial rate of reaction with all this data here?
I'm not exactly sure, but you would take the change in concentration and the change in time.
Okay, great. Good starting point. But we have 3 different concentrations that are changing. Here's some new voices. New voices, new voices, new voices. Savannah, go ahead.
Well, Tripty said it, and so I'm volunteering her to speak.
Your group's answer would be, or thoughts?
Would it be the slowest concentration, like the slowest one to form?
It might be, but not because it's the slowest one. Humphrey? What about the stoichiometric coefficients? How do we determine the initial rate of reaction? Which of the reactants or products do we look at, and why? Okay, so the whole thing you did in Activity 57, the whole thing you did in your homework, right? We look at what is the initial rate of consumption of, let's look at the green line, NO. Is that the rate of reaction? We find that rate. We have to divide that rate by the stoichiometric coefficient is 2. And that would be the initial rate of reaction. Negative sign, but it would be the initial rate of reaction. What about the initial rate of production of NO2? Is that the rate of reaction? Why? Stoichiometric coefficient of 2. So the easiest way to find the initial rate of reaction would actually be to find the rate of change of O2, the change in concentration over the change in time. And if we're talking about calculus, we're going to find the tangent to the line at the beginning, find the slope, the rate of change, right? And so we're going to be talking about the integrated rate laws starting in class on Wednesday, and that's your pre-class quizzes for Wednesday. We're not doing the calculus in this class. It is not a calculus-based class, but it is using the results of calculus, thinking about how rates of change occur in different rates of reaction, different orders of reaction, and using that to figure out some pretty cool stuff about how concentration changes with time. All right, so I want us thinking about stoichiometric coefficients, how that relates. If we then did experiment 2, what would we change about the first line here for experiment to get experiment 2? The initial concentration of which one would change? O2. And then would the initial rate of that reaction be the same or different? It would be different. Right? It would change because the change of the rate of that reaction is proportional to what the concentration of O2 is. How do we get experiment 3? If we start with this and change line 1, what would experiment 3 be? We'd leave O2 at point, is it 0.10 or 0.010 in the table? In the first table as well? Yeah, it is. Okay. We would do half the initial concentration of NO. And would the rate of that reaction, the initial slope of those lines, be the same?
No.
That would change 4 times because we changed the concentration 2-fold, and it's 2 squared. There's a difference in the initial rate. All right, so hopefully that helps you align a little bit what it is the differentiated rate law allows us to do. It says, if we change this and do a different experiment, what do we expect to see for the slope of this? Is it going to be influenced by the concentration or not? If it's not influenced by the change in concentration, it's 0 order. If the change in slope is proportional to the change in concentration, it's first order. And if it's an exponential change, then we're going to see an exponential difference in the rate compared to the change in concentration. Questions? Told you this semester was going to get pretty math heavy pretty quick, right? So we're thinking about proportionality, exponential, linear, logarithmic, inverse. We're going to start doing a lot of inverse stuff too. All right, so I think we've already gone through. What was the answer? What was the question?
To the time.
So what time did it was 8? It was 8? Oh, it was 8? Oh,
Initial rate.
Okay.
We'd want to do as close to the beginning as we can to get as close to the actual slope at the very beginning of this graph. So I'm going to say that if we do that calculation, look at the change in concentration over the change in time for O2. What's that change in concentration for the first 285 seconds? 0.0005 molar over 285 seconds, right? So that is our initial rate of O2 change. Why is it a negative sign? All right, so we are decreasing the concentration, so it's going to be a negative sign. If I say, what is the rate of consumption? We would have a positive sign. So actually, I'm unhappy with the way that this is written. If I'm saying, what is the speed of the car? Are you ever going to tell me a negative speed? If it's going from here to downtown or downtown to here, if I say the speed, then that's almost always a positive. If I say, how quickly is it coming towards me, and it's going the opposite direction, you would give it a negative sign. So the sign tells you the directionality of it, and we're actually going to change some of the slides here in a second. So I want you guys to determine which one of these is appropriate for the initial rate of consumption of NO relative to what we just found for the initial rate of consumption of O2. and I would advise you not to use the table to answer this. I would advise you to use this value to answer this question. Take about 1 minute. Raise your hand if you're stuck. Need some help.
So for the rate of that, you have to divide by the coefficient.
Can you pass that straight back to David? Red. Josh,
I think he said screen, right? He said screen.
All right, so how do we figure out what the initial rate of consumption of NO is, Kayla?
So we know the order of NO is 2 in comparison to the O2, so we just multiply what we got for O2 times 2.
So I like where you're going, but it actually, the rate order has 0 to do with the relative rate of consumption and production of reactants. So what the rate order tells us is more about the mechanism of the reaction, what's happening behind the scenes with the actual molecules colliding with each other. And this one is a much simpler process, actually. John?
For the stoichiometric values, we're going to utilize those since we know O has 1 and NO2 has 2. We want to multiply what we got for the initial rate of O2, and how we're going to kind of write it down is we're going to have the stoichiometric number of NO2 on top and the number of O2 on the bottom. That way the O2's cancel out.
So you're actually doing unit conversion. Nice. I like it. I am very happy with that. I think one of the simpler ways to talk about this that I think Activity 57 helped work you through, no, Activity 36, the one that you guys just got back, is during this amount of time, from 0 to 285 seconds, how much O2 was consumed versus how much NO was consumed. It was a 2 to 1, right? Twice as much of the NO is consumed as the O2 is consumed. That means the rate of consumption was double. And we can justify that because we have a stoichiometric coefficient, which doesn't always align with the rate order. So that's why I wanted to be a little bit careful with the rate order there, okay? So we know that that's true without looking at the table, just by looking at the stoichiometric coefficients. But we can back it up by looking at the data and seeing that that is actually true. So for every one of these that goes away, 2 of these is taken away as well, and 2 products are formed. So that is going to be directly applicable to the rate of reaction. So which one is that? I think you guys have different numbers and letters on your worksheet than I do. Don't you love when I mess with you guys? All right, and I think the reason it's 1.8 versus 3.5 is this is actually 1.7 something. But I had 2 sig figs. Is the appropriate number of sig figs for that? All right, questions? So what about the rate of production of NO2? A couple more seconds. All right, closing out. So Matt, what did your group discuss? Which one would be the rate of production of NO2?
Well, I think it has to be a negative number because it's production, not consumption. So we said it was 3.5. So C.
So why is that to be negative? Think about the concentration over time. Is it going up, going down, or staying the same?
I said production.
So
It's going up. So here's, and I totally botched it with the slides. Here's what I want you guys to think about the negative and positive side. Your workshop activity 57 specifically addressed this in the first page. If I say, what's the change in concentration? Does that say going up, down? It doesn't say either one, right? Change in concentration over change in time, you would have to include a sign to say that it's disappearing or it is being produced. How does this negate the need for a sign?
Production.
I say it's going up. With the last one too, I said it's being consumed. So you don't include a sign. If it says in the wording of the problem that it is going up or going down, you don't include a sign. It's all positive. It's like speed, right? Like how fast is the car going? Not what direction is it going. Overall speed. Lynn, not happy with that?
No. So if you don't directly say.
If I say, what's the rate of change?
Okay.
You have to give me a sign. If I say, it's going down, how fast is it going down? Don't tell me negative 27. Because then I already specified the directionality by saying it's going down.
So would you count off on the test?
I would just prefer you not do that. All right, last question. What is on this question? What is the initial rate of this reaction? Couple more seconds. All right, you guys are all over the place. Talk to your neighbor. Try to figure out which one of these is the appropriate rate of reaction.
Earlier, you said that it's going to be low because stoichiometric coefficient is 1, so the initial rate of consumption was that.
So that would be the difference law, not the actual rate.
It's not really,
Remember the rate
It just says that without specifying the name.
because if you're trying to find the initial rate, you take whatever other length of time you have to divide by the
All right. We've got a 50-50 answer here. I want to hear one from each side. What are the two answers we think we have? B and C. All right, which one's right? Why? Someone very confident want to share theirs? Which one and why? Ruby.
I think it's B, because that is the rate of consumption of O2, which has a stoichiometric coefficient of 1, so that's the rate of the reaction.
So if you guys have not already completed this packet, there is a definition in this packet of the rate of reaction. The rate of reaction is, what would the rate of consumption or production be for anything that had a stoichiometric coefficient of 1? We do not always have a reactant that has a stoichiometric coefficient of 1. So sometimes we have to say, well, there's a stoichiometric coefficient of 3. So if I know the rate of that being consumed or produced, I can divide that by 3 to find the rate of reaction. So if you haven't gone through that, make sure to go through that very carefully. And I think it was the beginning of Model 3, where it said that exact definition. All right. So in this problem, B is the rate of reaction based off of the previous couple questions that we had. Why does that not match up with what's on this. The top table. 1.0 times 10 to the negative 6 molar per second. Why is that not the same? Something's wrong. It's the exact same initial concentrations, exact same reaction. Is it the same temperature? 25 degrees. 25 degrees. Same temperature. What's going on? What's wrong? Moab.
The experimental conditions are different than theoretical ones?
Nope. In this case, we're using ideal conditions. So, not in this case. How did we determine the slope here?
Initial.
We said, well, I know it's a curved line, but let's just take 2 points on the line that are kind of far away from each other, the closest we can get, and let's find the slope of that curve by approximating it as a line. How do you find the actual initial? Calculus. Fantastic. So using calculus, we can actually find the slope of the line at any point in time, including the initial point in time. So this number that you have in the first table is a much more accurate version of the initial concentration. So this would be based off of our crappy slope calculations here. But if we could actually find the instantaneous slope right at 0 seconds, that's going to be a little bit different from what we actually calculated. Although I'd expect it's going to be the other way around, right? Should be steeper.
Okay, you said the definition of rate, or the definition of the initial rate is the stoichiometric. The one that has 1.
If there is something that has 1. We'll do a problem that'll get you onto that right now.
Okay.
All right? So, this is not a problem that's on your worksheet, but this is one I think it'll be useful. So just take that formula and make it a sentence. So every 3 that are consumed, 3 A's, how many P's are consumed, how many P's are produced. Put that in your sentence. Talking about the rate of. All right, I want to hear someone who put together a sentence relating the rate of production through the stoichiometric coefficients. You guys know what I'm talking about? Christina, give it a shot.
For every 3 A's that are consumed, 5 E's are produced.
All right, so when we put it into a sentence like that, it's not really very mathematical, right? You're like, well, 3 of these are used up, 5 of these are produced in the same amount of time. So if it's in the same amount of time, is the production of E faster or slower than A? Faster. Okay? And a lot of you did not think through it in that way when you were completing activity 36 or answering, I don't know if I had questions on the exam. I think it was 36 that I was grading, where you guys weren't necessarily looking at that, or 57 actually. So if you're talking about the relative rate of consumption and production, and you're not using logic, and you're telling me that 5 is formed slower than 3 is being consumed, then I want you to take a step back and think about what should the value be. And then the next question, of course, is what is the rate of production of E? Go ahead and click it in. So now instead of is it faster, slower, or the same? I want you to put in a numeric value for what the rate of production of E is.
Yeah, I mean, that makes sense. Sorry.
Make sure your number checks out. Make sure it jives with the last answer. There should be a faster rate of production than the consumption of it.
Oh, yeah.
I said invalid.
What?
Yeah, what? I got a next one here, bro. There's like, don't worry. It'll be in 20 minutes. That's what I just do. And they take after like, and they took it off. No, I just like because we use 3. Is that correct? No, but like we used to sleep for like 3 years.
All right, we have 41 responses. So if you guys can't see over here, for the clickers and on your calculator it's actually EE, but on clickers for some reason it's E. That is a substitute for times 10 to the. So if you want times 10 to the negative fourth, you do E minus 4. Does that make sense? All right, should save you some time. So let's look at our responses. Are they uniform enough where I can actually see anything? All right, so this response came also, I saw people putting 9.5 E minus 4, and that gives you that fourth response there. So how do we find that? Here is my tip. If you want to simplify your life when you're working with relative rates of consumption and production of reactants. Step 1, find the rate of reaction. What is the rate of reaction for this reaction? How do we find the rate of reaction for this reaction? Humphrey. So we're going to divide that by 3. What does that give us? Does anyone have a... And I would probably use... Oh, I guess it is actually 1.9 exactly. Molar per second. All right. Here's why this is so useful. If I ask you now to find what is the rate of production of D, what do we do with that number? It's 4 times bigger for D. So the rate of reaction multiplies out times 4 to find the rate of production of that. What is the rate of production of, or consumption of E? 2 times the rate of reaction. Okay? So what you guys were doing in activity 36 or 57, I can't remember which one, was you're looking at dividing by one stoichiometric coefficient, multiplying by the other. There's a lot of, like, you can flip it by accident, you might get a number that's bigger than you're supposed to or smaller. So I'd really advise always find the rate of reaction. Once you have the rate of reaction, you just multiply that by the stoichiometric coefficient to find the rate of consumption or production. And then if I say, what is the rate of change in concentration of one, you have to include this on. But I don't say consumption or production. Any questions on how that fits together? Bree?
Yeah, I thought it was defined in seconds. I think it makes more sense now.
Ah, yes.
Yeah, your math just didn't make any sense to me. I was really confused. I literally just realized it was seconds, though.
That doesn't really help, does it? Okay. My writing sucks. Okay. I'm going to skip this. And what time we got? We got 6 past. All right. This is called the iodine clock reaction. It is nuts. It literally goes from clear to dark blue to clear to dark blue. It goes back and forth. And it's an equilibrium reaction that is just kind of insane and very difficult to... It has like 6 steps in it. Literally you're pouring and it goes black, and then it'll turn white again in a second, clear. So we have a whole bunch of data here. I want you guys to determine the differentiated rate law for this reaction. Once again, we did different experiments. One set of data. We're just looking at someone calculated the initial rate using calculus. Second experiment, third and fourth. I want you to go ahead and type in the rate order for each one of our reactants. You know what I'm asking?
Tell me for the, you talking about K times and concentration?
So we have reactant 1, reactant 2, reactant 3. Can we just say the rate order is 1, 3, and 2? No, we can't just pull in the stoichiometric coefficient. So I want you guys to find, with all these different experiments, type in what is the rate order for these three, type it as a 3-digit number, and hit send. Alright, so I want you to find all 3 rate orders, send them in sequentially in number. Once you have that, you can find the rate constant as well. Go ahead and try on your own. Raise your hand and ask for someone to come around and help. There's a few of us still here.
Oh, that's yeah. Okay, that's
All right, we have 39 clicks. I assume that means we're doing all right. So to find the rate order for hydrogen peroxide, which 2 experiments do we want to compare? Marlene, did you want to take a stab at this?
For the first one, I use experiment 1 and 2.
Okay, so between experiments 1 and 2, concentration of I minus is the same, H plus is the same. The only thing that changes is the one we're interested in. So we double the concentration of H2O2. What happens to the rate? Doubles as well. So that's what order? First order. All right. What about for I minus? Josh, how did you find the rate order for I minus?
I use experiment 1 and 3.
Okay.
Because the other stayed the same. It doubled there, and the rate doubled there, so it's stayed 1 as well.
First order. All right. What about for H plus, proton hydrogen ion concentration? Who wants to describe that? Bria.
I used 1 and 4.
Okay, 1 and 4.
The same. And the rate order stayed the same, so it was 0 order.
Great. 0 order. Can we find the rate constant then?
Yeah.
Which experiment do we use to find the rate constant? So I think I have all this written out really slow, but you guys are crushing it. So our rate, differentiated rate law is this. Why? What am I missing? The concentration of H plus to the 0 power. What is anything to the 0 power? 1. So we don't even write it. So you know it's there. If you ever see a reaction, it is only reactants and all reactants that are in the rate law. But if they're raised to the 0 power, then you don't write them. Okay? So whenever you look at any reaction, know that you should see all reactants, the concentration of reactants. All right? And then can we find, you guys said that we can find K? All right, I'm going to let you guys do that on your own. I'm going to have one last question before you go. All right, what is the rate order for this reaction? You guys got this, right? Wait, what? So, a little foreshadowing for next class. This is what you need integrated rate laws for. Calculus is our friend. Integrated rate laws find that you can plot how concentration, or radioactivity in this case, changes with time. Moab. Thanks. You can look at exactly how concentration changes with time, but that might give you, this is what that graph would have looked like if I plotted that concentration versus time. I'm calling it radioactivity here. You guys did in week 1 of your lab, is that right? You found the natural log of a number. Did you do this yet?
Totally remember.
You found 1 over a number and just made a table out of all of those. And so what you'll be doing in your labs coming up is you're going to be plotting how concentration changes over time and looking at, does the rate of change of that reaction change as the concentration goes down? Think about what would happen for 0 order, first order, second order. And we're going to be plotting natural log of concentration versus time, and 1 over concentration versus time. That is what you guys have to look forward to for your pre-class 101. Find out on Wednesday, unless you can figure it out on your own. If you have not already collected your exam or activity 36, please do so. Moab.
I'm first in line.
Can you do me a huge favor real quick, Logan? Can you give this to the girl in the Adidas hat, please?